I'll be admitting students as we continue. And therefore, I've started the recording. We will make the recordings available like we did last time at the end of this lecture. Today, I want us to look at the periodicity of elements of the periodic table. And when we talk about periodicity, we will be looking at how the properties of these elements change as we move from one element to another in the periodic table. I've talked to you about the electronic configuration, and we have also done some classification of the elements in the periodic table. And we have grouped them into S block elements. We have the P block elements. We also talked about the transition metal elements, where we had the D block elements, the lanthanides, and the actinides. So we are saying that when you have elements in the periodic table, they have going to behave in a manner that the properties are going to depend on the group into which they are placed, and also onto the period into which they are placed. And therefore, we say that elements in the same column, when we talk about the same column, these are elements in the same group of the periodic table, will have similar chemical and physical properties, and they have similar valence shell electron configurations. And this similar valence shell electron configuration means that they have the same number of valence electrons, and that these valence electrons are going into the same orbital types, and these orbital types are going to be of different energy levels. You remember when we talk about the S1, we have 1s1, 2s1, 3s1, 4s1. These are the group 1 elements. And then they have got the only valence electron entering into the s orbital. And therefore, when we say that they have the same number of valence electrons, for example, I've said that S1, 1s1, 2s1, 3s1, 4s1, 5s1, it means that we have only one electron, valence electron. Entering to the same orbital type means that they are entering to the s orbital, and that the orbitals will have energy levels that are different. A 1s orbital, a 2s orbital, a 3s orbital are orbitals of different energies, as we explained in our previous lectures. Now, the slide that I'm showing here is giving the different groups of the elements in the periodic table. The one is, the S and the P block elements. Group 1 and 2 are the S block elements. Group 13 all the way to 18 are the P block elements. Then we have talked about the D block elements, the lanthanides and actinides, just as I have already explained. So you are already aware of the different groupings of the elements in the periodic table. Okay. Now, when we talk about the periodic trends, we want to look at the atomic parameters. And when we look at the atomic parameters, we are looking at issues like the effective nuclear charge, which I'm going to explain to you what it is, the atomic radii, ionization energies, electron affinities, and electronegativities. That is actually what we're going to confine ourselves into in today's lecture. Now, when we talk about the periodic trends, then we think about the periodic law. And this states that when the elements are arranged by atomic number, then their physical and chemical properties vary periodically. And you know that the elements in the periodic table are arranged in order of the increasing atomic numbers. The atomic properties such as the effective nuclear charge, the atomic radius, the ionization energies, electron affinities, and electronegativities are very important parameters that account for the chemical properties of an element. And when we talk about the effective nuclear charge, this is defined as the net positive charge that an electron experiences from the nucleus. And this is equal to the nuclear charge of that particular element, but it is reduced by factors such as the shielding, the screening, or the electron repulsions that result from multi-electron atoms. So the effective nuclear charge is the net positive charge that is going to be experienced by not only the valency electron, but any electron that we have in the configuration. And it is calculated by a formula where we say that the effective nuclear charge, which is ZEFF, is equal to Z. Z here is the number of protons that we have in that particular electron, in that particular atom. So what you have here is the effective nuclear charge. This Z here is the atomic number, and the S is what we call the Slater screening constant. The Slater screening constant is actually the shielding effect of that particular electron, and it is calculated using some rules. Here we are simply saying that is the number of shielding electrons. The number of shielding electrons, each of those shielding electrons is going to have a particular screening constant. And then you look at the total number of the Slater screening constant, which you subtract from the atomic number of the element, and that is going to give you the effective nuclear charge of any electron that you can talk about. So you can talk about the effective nuclear charge of a d electron. For example, if we are talking about iron, you know, iron is going to have some 3d electrons. So those 3d electrons, then each of those electrons will have a particular effective nuclear charge. But because they are all in the same 3D, then we can pick any electron in the 3D and then look at how much shielding that any of those electrons is going to have as a result of the 4s electrons, as a result of the 2p electrons, the 2s electrons, and the 1s electrons. And when we calculate all that, we are going to get the total shielding effect. And that shielding effect is subtracted from the atomic number so that we can get the effective nuclear charge of any electron. It is not a requirement in this unit for us to take you through that calculation. And therefore, for purposes of this, I'll just give this equation and we move on. Okay, now trends in the effective nuclear charge. And we say that when we move across, that is from the left to the right of a periodic table, when you move across a period, you find that an extra proton is added to the nucleus. When you are moving from lithium, you are going to boron, carbon, so forth, you find that you are increasing the number of protons, and therefore the nuclear charge is increasing, which means that the effective nuclear charge is also going to increase. Therefore, as you move across a period, the effective nuclear charge increases. What happens to the effective nuclear charge as you move down a group? As you move down a group, the effective nuclear charge decreases. Why does it decrease? Although down a group you have increase in the number of protons, you have increase in the atomic number, you find that that increase is countered by an increase in the energy levels. You have extra layers that are being introduced as you move down a group. And therefore the increase in the number of protons is counteracted by the increase in the energy levels. And this counteraction means that as you move down a group, the effective nuclear charge decreases. And what you can see in this particular table is across the period. Across the period, for example, you can see from lithium to beryllium to boron to carbon, these are elements in the same period. And as you move across the period, you realize that the effective nuclear charge is increasing, as illustrated by the numbers that you can see here. So you realize that it is increasing in that particular direction. Now, as you go down a group, the effective nuclear charge is decreasing. For example, from beryllium, going downwards, you find that you have 3.68. When you go to a 2s electron, a 2s electron is going to have a less effective nuclear charge. So this is because of the shielding effect, and I want to discuss that shielding effect in details as we go on. Now, the shielding, that's what I want to discuss, is experienced in atoms with more than one electron. We cannot talk about shielding, for example, in hydrogen, because in hydrogen, we've got only one electron, and that electron is found in the 1s orbital. It doesn't have inner orbitals. It doesn't have other electrons. And therefore, we say that in atoms with more than one electron, there is what we call the effect of electron-electron repulsion, which depends on where the various electrons are located within an atom. And if I can illustrate that, now you have that one as the nucleus, and then around the nucleus, you have, for example, that is the first energy level. Now, that first energy level will have an electron. So you will have, want to pick a different color. So you'll have an electron here, and you have another electron here. When you have these two electrons, then they are going to have what we call electron-electron repulsion. And that electron-electron repulsion is going to affect the nuclear charge that these electrons are going to experience from the nucleus. And therefore, the electron-electron repulsion is one of the factors that are going to lower the effective nuclear charge. Now, we also have electrons in the outer nucleus. And when we talk about electrons in the outer nucleus, if I had, sorry, just want to do away with this. How do I do that? I want to undo. If I had another energy level there, this energy level is also going to have some electrons. So you can have electrons, sorry, I don't, so you're going to have electrons here, electrons here. Now, what happens here is this, that these electrons here are shielded by the electrons here. And that means that the nuclear charge that is going to reach this electron that I'm showing here is going to be reduced because of, number one, these electrons in the inner energy levels will shield the full force of nuclear attraction that is going to reach this outer electron. And number two, the electron-electron repulsion of these electrons here and also of the electrons in the second outer shell, in the second energy shell, are going to have an influence on the effective nuclear charge. And that is why we are saying that electrons in the outer shell are pushed away by electrons in the inner shell. In other words, these electrons here are being pushed away by electrons in the first energy level. And as a result, the net nuclear charge or the effective nuclear charge that the outer electrons are going to experience is going to be substantially lower than it would experience if there was no shielding by the inner electrons. And we say that the outer electrons are shielded from the full charge of the nucleus by the inner electrons. It is very important to note that electrons in the same energy level will have an immediate shielding in the nuclear charge. What do we mean? The nuclear charge of this electron here is the same nuclear charge, the effective nuclear charge of this electron, because these are electrons in the same energy level. Electrons in the outer shell cannot shield the nuclear charge from electrons in a lower shell. We are saying that these electrons here cannot have any shielding effect on the electrons in an inner shell. But electrons in an inner shell will have a shielding effect on electrons in an outer shell. That is what we mean by that particular statement. The trends in the shielding, we say that the shielding of the outer electrons will increase as you go down the group. And this is because of the extra energy levels that we had as we go down a group. As you go across the period, the shielding does not increase. Why? It is because as you go down a group, we are not adding any extra energy levels. It is only extra electrons that are being added to the outer level of the electrons as you go across the period. Remember, as you add an electron, you are also adding a proton. Therefore, we don't expect the shielding to increase as you go across a period in a periodic table. Let us talk about atomic sizes, atomic radius. Now, when an atom does not have a definite, we say that an atom does not have a definite size. But we can talk about the atomic radii in terms of the distance between the nuclei of two adjacent atoms that form a covalent bond. And therefore, we are defining it in terms of the covalent radii. It is the maximum in the radio distribution function of the outer shell. And here we can illustrate this way, that we have an atom here, and we have an atom there. These two atoms are defined by a particular nucleus, a particular nucleus. So the distance if we get that one, is going to give us what we call an idea of the atomic radius. So we say that it is the value for that atom in a set of covalent radii assigned to atoms in such a way that the sum of the covalent radii of the atoms A and B predicts the approximate length from A to B, which I'm actually illustrating from A here to B. Okay? When you talk about the atomic sizes, we need to look at the atomic radius. Yes, somebody is asking a question. Please go ahead and ask that question.
Could you pardon on the atomic sizes, the previous slide?
Okay, I am here. Yes.
I've not understood the concept there.
Okay. we get it, I say that you have this, and you have an adjacent atom here that are covalently bonded. You know, my illustration is simply showing that they are touching each other, which in real sense is not true, but I'm using this for purposes of illustrating. Then you have the nucleus there, and you have the nucleus there. And the shortest distance between these two is this distance here from point A to B. And that is what we use to get the atomic radius. Now, what you'd expect here is this, that if you are talking about atoms of the same element, this one and this one would actually give you an impression that the distance from here to here is equal to the distance from here to here. And therefore, if you get a half of this distance, then it is going to give you that particular atomic radius, if we are talking about atoms of the same element, okay? If we are talking about atoms of different elements, then I'm going to show you a different way of calculating that. I think it should be part of my presentation here as we go on. I'll be able to illustrate that. Is it clarified?
Yes, thank you.
And I would encourage students to do like she has done. You stop me at any point and you ask questions so that we can clarify as we go on. So what are the trends in the atomic sizes? When you go down a column or down a group, the atomic radius is increasing. And this is due to the increase in the number of shells as we go down a group. What happens when we move across a period? You'd expect the atomic radius to decrease because of the increase in the effective nuclear charge. That's how we can explain it. Now, this one here is explaining what is happening as we move across a period. So you find that from hydrogen to helium, there is a decrease. Now, from hydrogen to lithium is down a group, you know, is down a group. And you realize that it is increasing from lithium, from hydrogen to lithium, to sodium, to potassium, to rubidium, and to cesium. This here we are going down a group. Now, but now within each, we have a period. So from lithium, we move across the period all the way to neon. You realize that the atomic radius is decreasing. From sodium all the way to argon, we have a decrease. From potassium all the way to krypton, we also have a decrease in trend. From rubidium all the way to xenon, we also have a decrease in trend. And that one has to decrease because of the increasing effective nuclear charge. Okay.
Yes, we.
You need to understand that I'm teaching from home, and therefore you expect disruptions from the other members that we have. Okay, go do that. Please go watch cartoon. So here we are showing the periodic table, and we have values that are showing you an impression of the periodic trends. And what you can see here, we have an upper value for every element. You have an upper value, that is the atomic number. The lower value here is giving us the atomic radius. And so you can see, for example, in lithium, it is 167. These are picometers. Then we move to beryllium, it has reduced. You move to boron, it has reduced, and they are going to reduce as you go across that particular period. And then down a group, you're going to realize that we do have an increase in the atomic radius. We do have an example that we can use to explain that. Refer to the periodic table and arrange the following elements in order of increasing atomic radius. You can actually give this without referring to the periodic table, because what you need to ask yourself is, you have selenium here and tellurium. You have selenium here and tellurium, and from the arrangement, selenium lies upper, tellurium lies lower. So the question you would ask yourself is, between selenium and tellurium, which one is going to have a larger atomic size or atomic radius? You'd expect tellurium to be larger than selenium because tellurium lies lower in the group. Okay? Then you ask yourself, between selenium and bromine, here you are moving across a period. Which one would you expect to be smaller? You'd expect bromine to be smaller because it occurs to the, it is on the right of the period. And as you move across, you'd expect this one to decrease. What does it therefore mean? You are comparing selenium and tellurium, and you say that tellurium is going to be bigger. Then you compare selenium and bromine, and you find that selenium is going to be bigger. And from that statement, you realize that the bromine is going to be the smallest, followed by selenium, followed by tellurium. And therefore, you are going to have an arrangement that looks like what we have shown here. Okay. So in a similar argument, you can use periodic trends to arrange these elements in order of the increasing atomic radius. And you find that you have fluorine, chlorine, and sulfur in that particular order. Then when you are given selenium, sulfur, and arsenic, you're going to get this order. The argument is exactly the same as that we have argued for the previous case. Okay. Ionization energy. It is the amount of energy that you require to remove an electron from a neutral atom in a gaseous state, giving you a positive ion. Very good example is when sodium is losing its valency electron to give you sodium plus. The energy involved in that process is what we call the ionization energy. It is the first ionization energy because we are losing the first electron. If we lose a second electron, then we talk about the second ionization energy. And if we are able to lose a third electron, then we talk about the third ionization energy, and so forth. Now, this ionization energy is a measure of how easy it is for us to remove an electron from a neutral atom in a gaseous state. The higher the energy, the more difficult it is for us to remove an electron from that particular gaseous atom. So what is the trend? As you go down a group, the first ionization energy is going to decrease. Why is it decreasing? It is because, one, the effective nuclear charge is decreasing as you go down a group. And as the effective nuclear charge decreases, it means that that particular electron is loosely held. And if it is loosely held, it becomes easy for us to remove it. And if it is easy for us to remove it, then the ionization energy is low. Somebody is talking? Is that a question? Okay. So as you go down a group, the first ionization energy is going to decrease. the lower the ionization energy, the easier it is for us to remove an electron from that particular atom. And this explains why it is easy for us to remove electrons from metals. Metals have low ionization energies because metals are S block elements. S block elements, they lie to the left of the periodic table. And the left part is where we have a very low effective nuclear charges. Remember, effective nuclear charge increases as you go across a period. So we're saying that generally the ionization energy decreases down a group, but it increases across a period. And we have explained why. This one, it can be explained in terms of the changes in the effective nuclear charge. So the ionization energy is going to increase with increase in atomic number. And it is proportional to the effective nuclear charge divided by the average distance between the electron and that particular nucleus. And I want to say something here, students, when I am illustrating this. That if you look at the graph that I am showing you, you will realize that we are moving from hydrogen to helium. And you will see that the ionization energy here is increasing. When you are moving from lithium to neon, you'll realize something here, that as you move from beryllium to boron, and from nitrogen to oxygen, you are exhibiting some decrease. You know, it is supposed to increase as you move from lithium to neon. But there are two particular cases whereby it is decreasing from one element to another. And that is mentioned here. Small deviations occur between group 2 and 3, and between group 13, not 13, 5A and 6A, should be 15 and 16. Why is this one happening? It is because I want us to look at this element here. In 3A, this is the same as group 13. In group 13, you will have, if I can illustrate, just want to illustrate using this. You have something like this. When you talk about group 2, the arrangement of the electrons are such that you have an electron here. Let me undo this. You have an electron and another electron. That is an S2. That S2 is fully filled. And that is true for group 2 elements. Okay? Group 2 elements, we said that they are going to be having a configuration of S2. That is 1 S2. You are going to have 2 S2, 3 S2. The configuration of group 2 is going to be like this. And that means that the arrangement of the electrons is going to be of this nature. What did we say when a configuration is fully filled? When a configuration is fully filled, when the orbitals are fully filled, then we say that this is a stable configuration. Now, when you look at this configuration here, for example, in aluminium, you realize that you are going to have an extra electron here. Where is that? I want to pick something. Yeah, you are going to have an electron here. Now, this electron here, if I can show you this, why we have between beryllium and boron, between magnesium and aluminium, that's what I'm talking about. I'm only explaining this one here first. This one, I want to, I am explaining this trend here, this trend here, those two, that's what I'm explaining. And for us to understand that, beryllium is a 1s2, mean 1s2. Boron is a 1s2 to s1. That's how it is. Now, it means that this, let me choose this one is a stable configuration, and therefore it is very difficult to remove an electron here. Now, but when you have the boron here, it is going to be easy to remove the valency electron, because this valency electron here is fully shielded by inner orbitals, and these inner orbitals are fully filled inner orbitals, meaning that it will be easier for you to remove an electron from a boron than it is for you to remove an electron from a beryllium, because a beryllium has a stable configuration. A boron has the valency electron completely shielded by inner filled orbitals. It is the same thing that is happening here in magnesium and aluminium. Magnesium will have S2. For aluminium, we are going to have S2 and P1. This P1 is fully shielded by a completely filled inner orbitals, and therefore it becomes loosely held, therefore easier for us to remove it. And that is why we have a lower ionization energy for aluminium than it is for magnesium, and a lower ionization energy for boron than it is for beryllium. That's how we can explain it. The other one is between these elements here, this element here, and this element here. Okay, what is happening here? In groups 15 and 16, the same we can explain using the electronic configuration, and I want to explain this. When we have nitrogen, the electronic configuration of nitrogen is 1s2, 2s2, 2p3. That's nitrogen. Okay, and oxygen is I don't have a way of making them superscripts, so you'll bear with me. Oxygen is 1s2, 2s2, 2p4. And I want to illustrate this using the Hans rule. If you remember the Hans rule, So if I show you the arrangement here, and also the arrangement here, they are going to be different. And you will allow me just go slow. This is a p orbital, which has 3 degenerate orbitals. A p orbital, 3 degenerate orbitals. So what you'll find here is this, that in nitrogen, because we are only interested in how much energy is going to be involved in the loss of the 3p, 2p, and these 2p electrons. How are they arranged? The way they are arranged is like this. For the nitrogen, the 3 electrons are arranged like this. 1, 2, and 3. That's how they are arranged, and this is according to the Hans rule. For oxygen, the electrons are arranged as 1, 2, 3, and the 4th one is here. That's how they are arranged. When we look at these configurations and assess their stability, and you realize that this is a very stable configuration because this is a half-filled orbital. And we say that a half-filled orbital and a fully filled orbital is very stable. The 3 electrons here are arranged such that each of these degenerate orbitals has 1 electron, and they have a parallel spin. This one, we have this electron here. These electrons here are paired, and because they are paired, there is what we call the electron repulsion, and it is easy for us to actually lose one of these electrons, and that explains why it is easier to remove an electron from an oxygen than it is to remove from a nitrogen. It is the same reason why we will have it easier to remove an electron from sulfur than it is to remove the valency electron from phosphorus. It can be explained in terms of the electron configuration that a P3 is going to be very stable, and a P4 will have one of the degenerate orbitals paired. And when it is paired, then the electrons there experience electron repulsion, and therefore it becomes easier for us to lose 1 electron, meaning that the ionization energy in such a case is going to be low. Any question from that explanation? Okay, so we move. So I was explaining what happens here. And you will see it in this slide when you compare phosphorus. When you compare phosphorus here and sulfur, you realize that phosphorus is high, sulfur is low. Okay? Again, when you compare magnesium and aluminium, magnesium is high, aluminium is low. It is for the same reasons that we have just explained in the previous slides. So electrons can be successfully removed from an atom. And when you are removing more than 1 electron from an atom, then we talk about the first ionization energy, the energy responsible for the removal of the first electron. You talk about second ionization energy, the energy responsible for the removal of the second electron. And the third ionization energy, the energy responsible for the removal of a third electron, and so forth. And that is why we are saying that each successive ionization energy increases because the electron is removed from a positive ion of increasing charge. What do we mean? When you remove the first electron, Now, the number of electrons in that configuration reduces, but the number of protons remain the same. It therefore means that the removal of an electron increases the effective nuclear charge. And therefore, for you to remove the second electron, a higher energy is going to be required. Similarly, for you to remove a third electron, an even higher energy is going to be required. Therefore, the successive ionization energies increase as you remove the successive electrons. Okay? We are saying that we will exhibit a dramatic increase when the first electron is removed from a noble gas core configuration, because a noble gas core has a very stable configuration, and it is actually resistance to the removal of any electrons. Now, that one is explained in this table that we have here. Now, the metallic character. How do we assess the metallic character of the elements in the periodic table? Elements with low ionization energies tend to be metals. And here we are talking about the group 1 and the group 2 elements. And those with high ionization energies are actually non-metals. And you realize that on the left of the periodic table, those elements are going to be characterized by high ionization energies. They are also going to be characterized by high effective nuclear charges. And therefore, they are going to be non-metals. But within a group, you can have some varying trends. So this can vary within a group as well as within a period. And we are going to illustrate that. So here we are just arranging elements in order of increasing ionization energies. You have arsenic 33, bromine 35, and then SB, which is 51. And this is going to be explained exactly the same way that we explained effective nuclear charges, because the effective nuclear charges have a direct influence on the ionization energies. If the effective nuclear charge is high, then the ionization energy is high. Therefore, you can use the same principle to explain this arrangement. And then the same can be done for this. But let me talk about electron affinity. You know, electron affinity is the opposite of ionization energy. The ionization energy is the energy involved in the loss of an electron. Electron affinity is the energy involved in the gain of an electron. So the energy change for the process of adding an electron to a neutral atom in a gaseous state to form a negative ion is what we call electron affinity. And we say that a negative energy change is exothermic, indicating that a stable ion is formed. And the larger the negative number, the more stable the anion that is going to be formed. We are saying anion here because electron affinity is going to lead to a negative species. And a negative species is commonly referred to as an anion. A small negative energy is going to indicate a less stable anion. And a positive energy change, which is endothermic, will show that the particular species is unstable. And therefore, we can evaluate it on the basis of the electron affinities. So we have said that it is the energy required to remove an electron from an atom's negative ion. You see, both expressions are true. Because if you have a particular element, M, and then you add an electron, you are going to get M plus, M minus, sorry. This is the energy involved in the gaining of an electron by M. That is electron affinity. Now, if we look at the reverse process, then this negative ion is going to lose an electron. We are going to remove this electron from a negatively charged ion. The energy involved is the same. The only difference is the magnitude is the same. The only difference is the sign. Therefore, we can also say that it is the energy required to remove an electron from an atom's negative ion. The magnitude is the same. The difference here is going to be the sign, signifying whether the process is either exothermic or endothermic. We can also say that it is the negative energy obtained when a neutral atom picks up an electron. So addition of an electron to give you a negatively charged ion. Removal of an electron from a negatively charged ion to give you a neutral atom. So that is the same definition. Okay. Now we continue. Electron affinities in the main group elements show a periodic variation when plotted against the atomic number. And we say that the S and the P block elements are actually the main group elements. And just give me 1 minute so that I can handle something here. Sorry for that. So we are talking about the main group elements, and I say that the main group elements are the S and the P block elements. Their electron affinities show a periodic variation when plotted against the atomic number, although this variation is somewhat more complicated than it may be displayed for the ionization energies. In a given period, for example, the electron affinity races from the metal towards the non-metal. It races across the period in the periodic table. But we are going to have some sharp drops, just like we saw in the ionization energies for group 2A and group 5A elements. So the group 1 elements, these are S1, they have moderately positive electron affinities. Group 2A have a lesser electron affinity when compared to group 1A element. And what is the reason? It is because group 2 elements, you are going to be losing an electron, or you're going to be gaining an electron into a configuration that is already fulfilled. You are talking about an S2. How do you gain an electron into an S2? That's going to be a little bit difficult. With the exception of the group 5A element, the electron affinity tends to rise across the period. No stable negative ions of group 18 elements have been found. No, I showed you different ways of naming the groups of the periodic table. The long form and the short form. So when I'm talking about 1A, 18, 13, 5A, 7A, 17, I think I'm using them interchangeably. Although at your level, you should be talking about the long form way of naming the groups of the periodic table. So across a period, the electron affinity will increase. And this is because of the increase in the effective nuclear charge. Down a group, the electron affinity decreases, again because of the decrease in the electron effective nuclear charge, which we explained because the atomic radius is increasing due to extra energy levels that we are adding. So generally we can say that the trend is towards a more negative electron affinities as we move from left to the right of the periodic table. But we can look at what is happening by group. Now, look at what is happening here. In group 1, you have 73, you have 60, you have 53, you have 48, you have 47, you have 46. So this is actually showing a general trend whereby it is decreasing. Okay? When you move across a period, now you have some variances. And where are those variances? For example, here, you have a negative value. A negative value here is telling you that it is resisting any additions because it is an S2, this is also an S2. Again, we talked about this one as stable configuration, and it is explaining why it is resisting any addition of an electron. And that's why we have a negative value here. If you look at the last column here, then you find that they are giving you 0 or negative values for the same reasons that we explained. And a trend is also shown here. I think you have seen this kind of configuration before when we are talking about ionization energies of elements in the periodic table. So you can see it is the same thing that is happening. Now, from what you know in a general way about electron affinities, state which member of the following pairs has a greater negative value. So this one you assess using the knowledge that we have given you, and at least here we have given the answers. So these are examples that you can interrogate during your free time. Now, electronegativity. When we talk about electronegativity, it is very similar to electron affinity in the sense that in both cases, an electron is being attracted towards a particular atom. Now, when we are talking about electronegativity, we define the tendency of a particular element to attract an electron towards itself in a chemical bond. And we can illustrate this, for example, using the kind of bonding in hydrogen. When you have hydrogen bonding with another hydrogen, you realize that the electrons in this particular case, these are atoms of the same element. The electrons here are shared in the middle because the electronegativity of this hydrogen is the same electronegativity of this hydrogen, and therefore the electrons we say are shared in the middle of the bond. But now when you have hydrogen and it is bonding with chlorine, when it is bonding with chlorine, you will find that another moment, please, I handle a situation. Denver. If you give us something interesting, then you close this one so that I can finish something. Again, I'm sorry for that. Now, in this bonding that I'm illustrating here, these are atoms of different elements. And when you go to the effective nuclear charge, and you also look at their electron affinities, you realize that the effective nuclear charge of chlorine is very high, and therefore it has a very high tendency to attract an electron. And therefore, when it is in this bonding system, you realize that the one electron in hydrogen is pulled towards chlorine, meaning that the electrons are going to be shared in such a way that they will be closer to the chlorine than they are to the hydrogen. And therefore, we say that the electronegativity of chlorine here is higher than that of hydrogen because it has a higher tendency of pulling the bonding electrons towards itself. So it is a measure of the ability of an atom or molecule to attract electrons towards itself in a chemical bond. And the type of bond formed is determined by the difference in the electronegativities between the two atoms involved. A very good example again here is that, the bonds that I'm illustrating here are covalent bonds. But these covalent bonds are going to be different in the sense that in hydrogen and hydrogen, the electrons are shared in the middle. And we end up getting what we call non-polar covalent bonds. However, in hydrogen chloride, the electrons are going to be shared closer to the chlorine, meaning that chlorine is almost gaining an electron, but it has not fully gained. Therefore, it becomes partially negative. We say that it is partially negative because it is almost acquiring the electron in the bond. Hydrogen, on the other hand, is almost losing an electron because that electron is moving very close to chlorine than it is to the hydrogen. And therefore, it acquires a partially positive charge that introduces polarity in this bond. And therefore, we say that the bond formed here is a polar covalent. And that's why we are saying that the type of bond formed is largely determined by the difference in the electronegativities of the atoms that are involved in the bond. When electronegativity when the difference is large, then we have a polar covalent bond. When the electronegativity is small, the difference is small, then we have a non-polar covalent bond. But when the difference is sufficiently large, then there's going to be a complete transfer of an electron from the less electronegative to the more electronegative, and that occasions what we call an ionic bond. How are the trends in electronegativities in the periodic table? When you move across a period, the electronegativity increases because of the increase in the effective nuclear charge. When you move down a group, the electronegativity decreases, again due to the decrease in the effective nuclear charge. You remember, we started by defining the effective nuclear charge because all these trends actually depend on the effective nuclear charges. And that is illustrated in this particular slide that is showing you some trends from potassium to calcium to scandium to titanium, vanadium, chromium, manganese, iron. You can see the trend that we are getting. Now, I have mentioned different types of bonds. Ionic bond involves a complete transfer of electrons from one element to another. And that happens when there's a very significant difference in the electronegativities of the two atoms that are involved. A covalent bond is when the electrons are shared. And we can have two types of covalent bonds. Polar covalent bonds, which is formed when the bonding electrons are closer to one atom than the other. And I illustrated this when I talked about the hydrogen and the chlorine. Because hydrogen is less electronegative, chlorine is more electronegative, and therefore the bonding electrons are going to be closer to chlorine than they are to the hydrogen. Therefore, hydrogen becomes partially positive, chlorine becomes partially negative, and we end up having a polar covalent bond. When I showed the hydrogen and hydrogen, the electrons are shared in the middle because those two are atoms of the same element. They have the same electronegativity, and therefore the bond formed there is a non-polar covalent bond. When we talk about electronegativity, we say that it's a measure of the ability of an atom or a molecule to draw the bonding electrons towards itself. And that electronegativity is related to ionization energy and the electron affinity. The difference in electronegativity between two atoms in a bond is a rough measure of bond polarity. And that is what I explained when I said that the difference is very large. We are going to have an ionic bond because we have a complete transfer of an electron from one species to another. When the difference is large, then we say that the bond is polar. But when the difference is small, the bond formed is going to be non-polar. And this is a table showing some differences. For example, when you have hydrogen, the electrons are shared equally. The difference in electronegativity is such that 2.1 minus 2.1, because the electronegativity of hydrogen is 2.1, then you are going to get a polar covalent bond. Look at chlorine. These electrons are going to be shared equally. And if you look at the difference in the electronegativity, you have 3 minus 3, which is 0. You get a non-polar covalent bond. Look at hydrogen bromide. Hydrogen bromide, you have a partially positive for hydrogen, partially negative for bromine. The electrons are going to be shared unequally because they are going to be closer to bromine than they are to hydrogen. And when you get the difference in the electronegativities, you're going to get this value here. And the bond that is going to be formed is polar covalent. Same thing to hydrogen and chlorine. It's polar covalent. But now when you have sodium and chlorine, we are going to have complete transfer of an electron from the sodium to chlorine, forming sodium chloride. And the bond formed here is going to be ionic. So we have explained that. Very important for you to distinguish. So again, polarization and distortion of the orbitals when the electronegativity differences are large. We will revisit this later on when we are talking about the bonding theories and illustrating how these ones can occasion changes in the bond shapes and the orbital shapes. Again, this is an example which is using electronegativities, arrange the bonds in order of increasing polarity. How do we do that? Just get the difference. Now, if the difference is very small, then the bond polarity is very low. When the difference is very large, then the bond polarity is very high. And therefore, I want you to look at this. You are given, for example, sodium and fluorine. The electronegative for sodium is 3. That of fluorine is 0.9. When you get the difference, you are going to get 3.1. Carbon and nitrogen. Carbon is given here as 2.5. Nitrogen is given as, where is nitrogen? As 3. When you get the difference there, it is what? 0.5. For oxygen and hydrogen, you get the difference, you find that it is 1.4. So you just look at the differences. The smallest difference is that of 0.5. This is going to have the least bond polarity, followed by the one that has 1.4, followed by the one that has 3.1. So you are simply arranging the bond polarities depending on the values that you get when you get the difference in the electronegativities. And you get this answer here. So there's an exercise that you can do on this particular textbook on these questions. Any questions from the students? Any questions from the students? Okay, if there are no questions, then I'll give some announcements. And then after the announcements, I'll take the record of attendance, after which I will release you. Okay? Announcement number 1.